Very well. Okay. So finally, as promised, we formulate the principle of minimum energy for stable equilibrium and calculate the governing partial differential equations and boundary conditions for a first gradient continuum. Okay. Tomorrow with Ivan Giorgio, you will please remember that Ivan is the family name, given name, and Giorgio is the family name. Okay. It is very strange because usually Giorgio is a given name. So when you talk with Ivan, you need to ask him which is your family name and which is your given name. Okay. Ivan, Giorgio will give you some basic ideas about how to use this principle with a computer software, which is COMSOL. I think that some of you already met this software, but I think that you need to become very skilled with it, because as I will prove today, it is a fundamental tool for every kind of design. And I think maybe not exactly COMSOL, but a similar evolution, a software which is evolving from COMSOL will become a standard in engineering design. So I think it is very important that you understand the structure of this software and the mathematical ideas behind it. Okay, so we have a functional. We already have introduced this idea in the last lectures. So you have a function which gives you the change, the placement of the body. You know, here I am confusing the mathematical model, the word for the mathematical model with the word used for the physical object. Okay, so be careful. Sometimes, even if I promise you to distinguish between the mathematical object and the physical object, I am confusing the names. Okay, so we have a placement of our body, and we decided that a reasonably detailed measure of deformation is given by C defined as F transposed F. Okay. Why I want to say reasonably detailed measure of deformation? Because there are mechanical systems in which the measure of deformation has to be described mathematically with other fields. For instance, we are working with Erden to a theory for a specific class of materials in which the deformation is not reasonably with F only. You need to consider also grad F. So the energy does depend also, these are called second gradient materials. If grad F needs to be introduced. So once more, even if it may appear to you crazy, okay, I want to underline that every theory has a very limited range of applicability. Okay, so you should not believe that what we are doing now is the theory of every continuum system. This is the theory of a specific continuum system. Okay, for sure, Otar, this cannot be a theory describing with a continuum model a galaxy or even the interstellar powder or even a planetary powder, you know, as they call it. So this can be applied only for a specific set of materials and for specific sets of phenomena. Okay. Now we have introduced, if you remember, the density of deformation energy. Of course, this density of deformation energy is not a generic function of F. It has to be a specific function of C. Okay, but as C depends on F, in the next discussion, we will, for simplicity, I mean, for making simpler calculations for the moment, we will use this structure for deformation energy. Then the deformation energy for your body is given like integral over C star, the reference configuration of W of F d volume. This is another assumption. Okay, and I underline that this cannot be generally valid. So what means this assumption? For instance, we are excluding that there is a surface, better to say a material surface, on which the deformation energy is concentrated. Okay. I'm sure that you have studied Laplace law, or at least you have heard about Laplace law. If you have of water and you have so this is water, and around it you have water vapor. You have seen that Laplace understood that the pressure inside is bigger than the pressure outside, and that the pressure inside is equal to the pressure outside plus surface density of energy concentrated on the surface of the drop divided by 2r, where r is the radius of the droplet. Okay. So this is called Laplace law. So we know that there are some physical situations in which you have a material surface on which you have concentration of energy. Okay. So we are excluding this. Why? Because this functional, being a volume integral, the integral on a volume on a surface of a volume integral is 0. So with this assumption, we are not excluding the possibility for describing this kind of phenomena. So this phenomenon is excluded in the applications of first gradient theory. Okay. However, the range of applicability of what we are discussing now is rather wide. So I think that the greatest part of engineering applications for the moment are based on this kind of continuum theory, which doesn't mean very much. Why? Because as we developed one model, we are using only it. This is the big problem. You know, somebody says that studying more general theories is useless because all applications are limited to the theory which we are describing now. Okay. This argument is rather stupid. If we were saying that as the vaccine for coronavirus is not used up to now, we don't need to study how to build this vaccine. You know, we simply up to now never managed to find important applications to continuum theories which are not first gradient theory. Okay. Okay, now let's proceed in studying this simple theory. So we have the body C star. We have, I think we called it C star 1 and C star 2, boundary of C star 2. The two parts of the boundaries of the boundary. So the boundary of C star is the surface surrounding C star. And C star 1 is a subset of C star. C star boundary of C star 2 is a subset of the boundary of C star. And when X belongs to C star 1, you say that the placement of X is exactly X, so there is no displacement. And when X belongs to C star 2, you have that key of X is equal to X plus U0 of X, and this is a given function. Okay, and it is you can say that this is U0 of X is the imposed displacement. Okay, so some engineers like to call this kind of, we are imposing boundary conditions. And some engineers say that this kind of boundary conditions are imposed by hard devices. Okay. So sometimes you will hear people talking about hard devices. Okay, these are devices which impose the displacement, whatever it happens around them. Okay. So we must find the placements verifying one, let's call them star, the boundary conditions star, and two, minimizing the total energy. In this case, the total energy is equal to the deformation energy. So, which is our mathematical problem? Find key defined in C star having values in E3. Okay? Such that key verifies star, which are called essential boundary conditions, because these boundary conditions limit the set where energy has the minimum. So you boundary conditions which we are imposing telling that the placement is given in some parts of the boundary. These boundary conditions determine the domain of the functional. So where the set where you are looking for minima. And this is the reason for which they are called essential boundary conditions. So find key such that key verifies this and such that EDEF is minimum in key. So in order to remember that we are looking for a specific placement and to keep key as a variable in the domain where the deformation energy is defined, we can call it key 0. So find a specific key 0 such that key 0 verifies the boundary condition and such that EDEF is minimum in key 0. Okay? Now, imagine to be Gabriel Piola or Lagrange. Lagrange died around 1800 and Lagrange died 50 years later. You don't have computers. You cannot do big calculations. So you must find analytical methods for finding minima. Okay. Now, what Ivan will teach you, will start teaching you tomorrow, is that in 2020, we can solve this problem with numerical methods. And there is already written software which can produce for you the equilibrium placement key 0. You simply need to tell to the software which is the energy. So the input of COMSOL are the inputs of COMSOL are 1, C star. You must tell which is the reference shape of your body. Then you must tell which is delta C1 and delta C2. You must impose give U0 of X. So you must give this. And you must write W of F. So the theory developed by Piola and Lagrange 220 years or 170 years later, exactly that postulation scheme is used for doing practical calculation. Okay, so we could stop our discussion now about the theory, and we could talk only about the computing tool, describing you how this computing tool works. Okay, this is what we could do. But why we can do it? because in this historical moment, we have powerful, very powerful computing tools, and we can work with them in order to get specific predictions using our theory. We can say, and the poor Erden knows how difficult it is. Given an energy, I can give you the predicted shape. Okay. Now, Erden was fighting with a very strange material printed at micrometers with measurements we are not sure how good quality they are, with geometries, because, you know, try to print something of some micrometers and you will see how precise you are, and try to shoot a picture of what is happening to your microstructure, and then you will see how difficult it is. So it was clear, I hope, to Erden, and now it will become clear to you. Maybe, Erden, you can organize a seminar during this class to the students describing what you did. Where are the difficulties? I mean, I think this is very important to show that I'm not talking about philosophy because I like it. You know, I like to waste your time talking about philosophy of science. You should, Erden, show to all the students the difficulties we are confronting and why all the philosophical questions I was asking are practical questions. If we want to open the modern engineering towards micro structures, structures having micrometer length scales, we need to understand how to deal with these new materials, new structures. So we need to understand how to adapt the available theory to predict what happens experimentally. So with these ingredients, Erden tried to have COMSOL producing some predictions which are in agreement with experiments. And he did not need to calculate the first variation of the deformation energy. Okay. So one could ask me now, why you want to teach us this obsolete mathematics? One could say that this is an obsolete mathematics. Okay, the reason I will try to explain in the next lectures. Analytical, numerical simulations work only giving one specific energy. Numerical simulations work with specific energy, not only with specific parameters. So you need some specific numerical parameters. And you can do simulations only with those figures. Now, when you don't know which are the right parameters, numerical computing is a little bit clumsy. It is a difficult tool. I mean, a tool which can be used with some difficulty. This is a possible answer. Okay, but let's move in the calculations and imagine that we are like Viola and Lagrange. The only computing tool which we have in our hands are a pencil and a sheet of paper, or, as we are modern, the screen of a tablet. Okay. So we have integral of W of grad key, the volume. I will not write the domain of integration when it is C star in order to be quicker. And this is the functional of which we must find the minimum. So replace here key 0, the function key 0, and find the minimum energy. This is what we need to do. Now, Lagrange, there are many theorems having the name of Lagrange. Lagrange gave a contribution to mathematical analysis, and mathematical analysis was developed in order to solve the problem of minima in continuum mechanics. For instance, I am sure that talking about a function of one variable defined in an interval, you have studied that maxima and minima, I am trying to draw the plot of this function. You have studied in mathematical analysis that the tangent to the plot of this function is horizontal, so the derivative of the function is 0 if you are in the minimum. So consider that this is a condition for a local minimum. You can have several minima. Okay, this is a local minimum. This is a global minimum in the plot which I'm drawing. Okay, so we can have several minima. So we can have several equilibrium configurations which are stable. Okay, this is obvious. Only for quadratic energies you have a unique minimum. Okay, in the very particular case of quadratic energies, you can say that you have a unique minimum. But in general, for non-quadratic energies, you have, in principle, several minima. Okay? So our aim is now to generalize the mathematical procedure developed for functions defined in AB having values in R to the case of functionals. Now, the reasoning I'm describing you now were developed by Lagrange. You know, Lagrange is the typical proof that you need a public education system. Lagrange was a young son of a noble family from Piedmont. Its Italian name is Lagrangia. But you know, Lagrange changed his name because it is more elegant to have a French name. And he was lucky because Lagrangia in Italian means the place where you are storing corn and hay for your horses in a farm. And exactly the same Lagrange, the same object is in French, is called with this Lagrange. So it was very easy for him to change the name from Italian to English. He did the reasoning I am describing, and I will try to describe you, when he was around 17, 18 years old, and he was a student in the Jesuit school in Turin. And he had a famous professor, a skilled mathematician. So this skilled professor understood how clever Lagrange was and directed his researches in the right direction. The father of Lagrange could not even understand anything about mathematics. And nobody in the family of Lagrange could have given him this education. So you need a system, a public system of education, giving to everybody the opportunity to reach the highest education possible for him. Okay, so which is the reasoning of Lagrange? I will try to reproduce it quickly, even if mathematicians could be very upset. Now, the idea is the following. You know that every function can be written with a Taylor expansion. Which has this form and I have truncated it at the second order. Okay? So what this is Taylor expansion. Remark that French are calling this truncated expansion because Taylor is English. Okay? While British people are using the description of the theorem. For instance, the theorem of existence and uniqueness of the solution for a linear system. They call it like this way. While in Italy and in France, we call it Rouchet-Capelli theorem because Rouchet is French and Capelli is Italian. You know, so this is the typical nationalistic attitude you find everywhere. So, however, I have the habit to call it Taylor expansion. So we keep calling it in this way. What is giving you a Taylor expansion? A polynomial approximating the function. You know, already Weierstrass proved a very elegant theorem. If you have a continuous function defined in the interval AB, and you consider the epsilon stripe around the plot of this function. So you consider the region in the plane, the stripe, is the set of function x, y, the number x and y, such that y is greater than let's call the function f of x. F of x minus epsilon is smaller than y, which is smaller than fx plus epsilon. So the epsilon stripe is this. And this is the epsilon stripe. What is below this is f plus epsilon, and this is f minus epsilon. Now, Weierstrass could prove that for every epsilon, you find a polynomial of order n whose plot is inside that stripe. Okay. He proved it with a very elegant reasoning, which is not allowing you to calculate easily the approximating polynomial. So Weierstrass proved the existence of the approximating polynomial. Okay. However, it didn't construct in an easy way the approximating polynomial. Now, tomorrow you will start seeing, or you will rediscover, that for numerical computation, it is essential to find the approximating polynomial for a given function. Now, Taylor is answering you when you ask about the approximating polynomial. Your question is, which is the approximating polynomial for a given function? Taylor tells you, calculate the derivatives of f in a point x0 and build the Taylor expansion. Close to x0, you get the required approximation. Okay. So, in a sense, Taylor expansion gives you an algorithm for calculating the values of functions. Okay. Now, I want to tell you, this lecture today is longer, so I want to stop with some lighter subject every 10 minutes, more or less. So don't believe, please try not to lose the discussion. Okay, so I repeat for you, we want to generalize the criterion of first derivative equal to 0 for functionals. And now I am reconstructing the argument which we have already studied in mathematical analysis. Okay. And I am reminding you that the Taylor expansion is the crucial tool for discovering that in a minimum, the first derivative of a function is equal to 0. While I'm talking about this, as I remember that tomorrow you will start playing another time with COMSOL, and as COMSOL uses polynomial approximating the functions, okay, so I am starting a small discussion about the concept of algorithm invented for calculating the values of functions. You are all young, so you have never seen the tables of logarithm. Okay. There were some printed books in which you could find pages and pages of numbers. These numbers were used for calculating the logarithm of numbers. Why? Because if you have a big number A, this is a computational problem. For the moment, it has only an historical meaning for you, but I think this is very useful for understanding how computers are working. So you have a big number A, and you want to multiply it with another big number B. And this product is very large. So what to the power alpha, and B is e to the power beta. So you need the tables of logarithms for finding alpha and beta. Okay. Then you know that e to the power alpha times e to the power beta is e to the power alpha plus beta. So you have two big numbers. You calculate the logarithm, you get two small numbers. Okay. You can sum these two small numbers easily or more easily. And then you calculate the exponential. How? Using the logarithms, get out A times B. So some monk made a lot of calculations. He wrote the result of his calculations in a book, and you can use this book for doing quicker calculations. Okay. Now the question is, how do you calculate e to the power x? Or how you calculate the logarithm of a number y? The answer is use the Taylor expansion. The table of logarithms were calculated using the Taylor expansion. And the Taylor expansion, you see here, reduces every calculation to sums and products. Okay. So we can comment before we go ahead in this discussion that for a long while, humankind had not only slaves pushing stones for building pyramids or the mosque in Istanbul or the cathedral in Europe. We had also slaves calculating products, so spending their life in calculating products and writing the big books of tables for allowing the other people to invent the theories of the motion of the planets. So also among human beings, we had slaves working in science. We had a category of, we could call them slaves, or people doing a terrible, boring job, and people doing a more creative job. Okay, now let's go back to our Taylor expansion. And let us imagine to truncate it at the second order. So we are close enough to be sure that this equality, this one, is at least preserving the sign. I will tell you what I mean. So f of x minus f of x0 is nearly equal to f prime x0 x minus x0 plus f second x0 divided to x minus x0 squared. So we assume that x is close to x0 so that is so close to x0 that the sign of right hand side is the same as the sign of left hand side. Okay, I think that you have heard the theorem of permanence of the sign in a limit procedure. So when x is close to x0, and if the Taylor expansion is applicable, this is true. This left hand side and this right hand side have the same sign. Okay, so imagine that x0 is a minimum. Okay, what it means? That is a local minimum. So close to x0, fx is greater or equal to fx0. So fx minus fx0 is greater or equal than 0. Okay. Now you understand local minimum. We are understanding why invented virtual displacements. So this reasoning is essential if you want to understand the logical source of the concept of virtual displacement. Okay? So you write x like x0 plus delta x, where delta x is small. You write delta in front of the symbol of the variable you are varying a little bit. Okay? So you have that f of x0 plus delta x minus f of x0 is greater or equal than 0. So what you have? You have that f prime of x0. What you have here? X minus x0 plus 1/2 f second of x0, x minus x0 square is greater or equal than 0. Okay? So what we do? We remember that this is small. Okay? And when delta x is very small, so this is true for every delta x. So we can formulate this statement, which is up to now purely analytical, in this way. You take the minimum of f. You move the variable a little bit. So you move it from x0 to x, adding to x0 a small delta x. Okay? For x0 is a minimum for f if double star okay. So you understand that this virtual variation, imaginary variation from the minimum is necessary for testing the property of minimality of your x0. So this double star tells you change a little bit, change of the quantity delta x, the candidate minimum x0. Okay. This inequality has to be verified. And this inequality has to be verified for every delta x. I mean, this is nothing that stating this inequality, which is the condition of x0 is minimal and Taylor expansion. Okay. So now, if delta x is very small, this term here is negligible. I mean, this is the kind of reasonings which a mathematician will cause a mathematician to start shouting, because this is what we can call an heuristic reasoning, and a reasoning for finding a conjecture and then proving it with more rigorous argument. If delta x is very small, then you have that this inequality is verified for every delta x. Okay. now you have a number. You multiply this number times every small number, negative and positive, and this number has to be greater or equal than 0. Now, imagine that for a certain delta x bar, f prime of x0 times delta x bar is positive. Then you multiply f prime x0 times minus delta x bar, and you get a negative number. Okay. So I should not write the equal. So what this reasoning proves? That the only possibility for having that this condition is verified for every delta x is that, so this is equivalent to say that f prime of x0 is equal to 0. So you understand, I mean, this reasoning most likely has been invented by Lagrange. Or if not by Lagrange, it has been exploited systematically by Lagrange. So if you have a function for which a Taylor expansion can be written, truncated at the first order, and if this function has a minimum in x0, then its first derivative in x0 has to be equal to 0. Now, this result can be formulated without talking about small variations of the independent variable. However, to arrive at this result here, you need to start from this equality. From this equality, you deduce this other equality, inequality. Then this inequality produces double star, and this double star is verified for every small variation of the independent variable. So you could tell, in other words, if you are in a minimum x0, imagine to vary a little bit the independent variable. Then the first derivative of the function in x0 multiplied times this imaginary variation of the independent variable has to be always greater or equal to 0. This is the only possibility for having this double star verified. Okay? Then, as a consequence of this virtual variation of the independent variable, you get that the first derivative of f in x0 is equal to 0. And you get the classical standard condition for finding minima of a function. Okay? This is not yet ended, because as this is equal to 0, you are left with the second derivative, 1/2 f second x0 delta x squared greater or equal than 0. But delta x squared is always positive. So this derivative has to be greater than 0. Okay. So what you have proven that a minimum is characterized by this condition: f prime of x0 is equal to 0, and f second of x0 is greater than 0. This is a minimum. Then you have learned that you have also a maximum if this second derivative is negative. Okay? So we have reconstructed the minimality condition for a function defined in an interval having values in the set of real numbers. Okay. F prime of x0 times x minus x0 is the best linear function approximating f x minus f 0. Okay. So the idea is, can I find a best linear approximation for a functional okay? So this is the point. Erden, we are left only you and me in visual contact. Let's hope that also the others are hearing. Okay, so you agree, you are, I hope that you agree that I'm going very slowly, right? Is it slow enough in your opinion? Okay.
Yes.
So this point is not so easy. Now I will give you an easy, I will calculate for you the best linear approximation for the deformation energy functional as if it were an easy thing to do. But the story is not, shows that this idea was not so trivial. Euler, who was elder than Lagrange, something I think that he was 20 years elder than Lagrange, could not develop the reasoning we are going to present now. And he received a letter by Lagrange. You know, Lagrange was trained by Jesuits. So he was younger. He had a good idea. He knew that the biggest mathematician of his epoch had not succeeded in solving this problem. So what he did? First of all, he published in French the solution in a journal which was distributed everywhere in Europe. And second, he sent a very polite letter to Euler telling him that he wanted to ask if he agreed with his solution and if he had suggestions for improving it. Okay? And Euler was clever enough not to try to quarrel with the young mathematician. He answered that he had some partial solutions to the problem and that he was very happy to postpone the publication of his partial solutions until another paper by Lagrange was published. Okay, so at the end of the story, the two Euler gave the star of quality to the result of Lagrange, and now we call the result, I will show you, the Euler-Lagrange conditions. Okay. Now, let's go in the technical details. I have the deformation energy written like that. Okay. And following the reasoning which we developed for functions, what we do? We write the deformation energy for the function key plus delta key minus the deformation energy for the function key. So think about our body. This part is blocked. This part moves there. Okay? And now we want to find the shape key 0, verifying the imposed boundary condition and minimizing the deformation energy. Okay? Now, the idea of Lagrange is the following. Key 0 is such that if I vary a little bit the shape, this inequality is verified. Okay, so key 0 is a minimum for deformation energy if and only if the deformation energy calculated in key plus delta key minus the deformation energy in key is greater or equal to 0 for every delta key. Now I ask you a rhetoric question. Are you surprised that we need to talk about virtual displacement? If I want to test the minimality of a function, I need to consider the candidate minimum. And then I need to change a little bit the candidate minimum with a small added displacement. Okay. And I must verify that when I change key 0 a little bit, the deformation energy can only increase. So there is nothing strange in talking about virtual displacement. Okay. In fact, now we will write this inequality in the following way. We write integral over C star of W grad chi plus delta chi minus integral over C star of W of grad chi. Okay? Chi zero, chi zero. And we make some transformation of this formula. Okay? Erden, you are there? You follow this?
Yeah.
Okay. I'm sorry, I don't see any other face, so I cannot ask anybody else. So you are my victim today. Okay. No, it is a joke. Many years ago, there was a PhD student who came with me to the lectures, and the students pulled his leg in this way. They said that I was paying him for having at least one student who was obliged to follow my lectures. So, Erden, you are the victim of this year. Okay. So we have that the difference of integrals is the integral of the difference. This is the a standard property of integration. Okay. Now we have here Lagrange idea. You have the integral of the difference of two functions. So Lagrange thinks, look, I have this function, which is the integrand okay. So let us study for a while. This is the what is called finite increment of the integrand. So the very crucial idea is included in the following steps. First of all, grad of chi zero plus delta chi, I can write like grad chi zero plus grad delta chi, because the gradient of the sum is the sum of gradients. Okay. We agree with this, right? Then we have a very crucial point. If I have a small quantity, is its gradient small? This is the most delicate issue which we have now. So imagine to have a function which is in the stripe. This is minus epsilon plus epsilon. So you have the function 0. And you have the stripe epsilon minus epsilon. This function here is very small. However, its derivative is not small. Because here you have big derivatives, right? I mean, you can easily see this point. If I build this function, it is continuous, and the derivative is discontinuous in this point, but you can calculate the integral of a discontinuous function in one point. And here the slope is very stiff, positive, and here you have a very stiff slope, negative. So in general, this is not true that you can commute the delta with the gradient. So what you have to do, you must use a suitable set of functions. You use functions of which you are controlling not only the value, but also the value of the derivative. Okay, so you limit the set of admissible placements to those functions for which both the function and the gradient of the function and the gradient of the function are controlled. So for telling that, in other words, for telling that delta key is small, you need to know I don't know why I don't manage to write to know that both delta key and grad delta key are small. Okay, this is some mathematical theory which has been developed by Sobolev around 1950. So 150 years after Lagrange. But you know, Lagrange was aware of the difficulty. So when he writes this equality, he tells repeatedly, be careful. For doing this, we need a specific set of functions. Okay. Now, this discussion is not a purely mathematical discussion. Why? Because in COMSOL, you are choosing functions whose derivative you can control. So when you say that a function has a small norm, so it is close to zero, you mean that the value of the function and the value of its derivative are close to zero. Okay, so when building finite elements, you will need to remember this requirement. Okay, but we will come back to this point several times. So you can write this like grad key 0 plus delta grad key, or equivalently grad delta key, and they are both small, minus W grad key 0. Okay. Now the idea of Lagrange is grad delta key is small, then I can use a Taylor expansion for estimating W of grad key 0 plus delta grad key minus W grad key 0. Okay. So I write that this is nearly equal to dW over d grad key times grad delta key. Now, what this means, we must specify, and here we will be helped by tensor calculus, which we developed. So W of grad key, we can write like W of F I A. Okay, you remember F I A is the partial derivative of the ith component of key with respect to the eighth independent variable. Okay. So telling that W, the deformation energy, depends on F is equivalent to state that W depends on these real independent variables. Okay. So we can consider the deformation energy as a function of the coefficients of the components of the tensor capital F. Now, when you write Taylor expansion, you have a function of fx1, x2, xn real variables. I hope, but I will repeat for you the result. The Taylor expansion can be written in this way. You calculate f in a specific value for x, then you calculate the derivative of partial derivative of f with respect to the first variable. You calculate this in x1, 0, xn, 0 times x1 minus x1, 0 plus df over dxn x1, 0, xn, 0, xn minus xn, 0 plus infinitesimal of higher order. Okay, you remember this formula, right? It has been shown to you in every calculus second year. Now, I am lazy. I don't want to write these long formulas. So what I discovered, that I can call this X. X means a vector having n components. So I write f of x. Now x belongs to Rn equal f of x0. X0 is another element of Rn plus. Now, nabla f. What is nabla f? Nabla f is the vector having component df over dx1, df over dxn. I calculate nabla f in x0, and I have a vector. This vector has these components. What I've written here, the inner product of nabla f with x minus x0. So without changing anything, I can write the Taylor expansion in this compact form. Okay. Now, what is the placement key? We are starting to use the theory which we developed previously. Key is key of capital X, P, is small x p. It is the position of the material particle in the actual configuration. So you have key 1 x times small e1 plus key 2x small e2 plus key 3x small e3. This is key of xp. Okay. So displacement has 3 component functions. Key 1, key 2, key 3. And I can call it key I using small indices. So I can write key of xp equal key I ei using Einstein convention. Okay. So writing Taylor expansion for key I means that Fia is equal to del partial derivative of key I with respect to capital XA. Okay. So I repeated another time this reasoning. So now we have the integral over C star of W F IA plus delta Fia minus WFIA. And we write this equal to dW over dFIA delta Fia. Now, if you remember, when I calculate the derivative of a function with respect to a contravariant index, I get a covariant quantity. And when I derive something with respect to a covariant index, I get a contravariant quantity. So dW over dFIA is equal to PAI. This is a one-time contravariant with respect to A and one-time covariant with respect to I. Okay, this is wonderful. This is one of Piola stress tensor. I don't want to call using the nomenclature of Truesdell. He calls it, I think, a second Piola-Kirchhoff stress tensor. I call it Piola stress tensor, period. Okay? And this is the definition of Piola stress tensor. Okay? So when you have given W of F, P is equal dW over dF, using a little bit more ambiguous but compact notation. Okay? Very well. But now, this is not an equality. This is an approximation. Because we are neglecting here infinitesimals. Okay? So what we have done, we have delta deformation energy, the finite increment of deformation energy, capital delta, integral of W F plus delta F minus WF. And we are defining the first variation of deformation energy, which is integral of dW over dF delta F. So this is called finite increment, and this is called infinitesimal increment. Okay. Now I ask you a rhetoric question. While writing this formula, am I using linear mechanics, the mechanics of infinitesimally small deformations? If I have a quadratic energy, I calculate the derivative. It is a linear function. The linear function is like that. So the derivative of this is negative here, 0 here, positive there. So you have this. Okay. So if you have x minus x0 square, the derivative is 2x minus x0. Okay. And the derivative is 0 in only one point. And in the neighborhood of the minimum, you write that f prime of x0, x minus x0 is equal to 0 for every x. So let's call it delta x. Okay, but you can have this function, and the derivative is 0 here, 0 here, and 0 there. And in x1, x2, and x3, the three minima, you have that f prime of x1 delta x is 0, f prime of x2 delta x is 0, and f prime of x3 delta x is equal to 0 for every delta x. So this is a linear condition with a variable independent variable. So we are not studying linear small deformations of our body. This condition is valid for infinitesimal increment starting from every key 0. Okay, and imposing delta deformation energy, which is a function of k0 and a linear function of delta key equal to 0 for every delta key, means that this is variable, this is unknown. Exactly as happens when you have x square logarithm of x plus exponential of x, and you calculate the first derivative, and you impose it is equal to 0. In general, you may have more than one solution and more than one local minimum. Okay. So minimality for the deformation energy in the set of admissible placements. So remember, one controls the placement and its derivative. Okay. Implies that the first variation of deformation energy, we have essential boundary conditions which are imposed. The first variation of deformation energy is given by dW over dFIA delta FIA. And this has to be equal to 0 for every delta key I. This is a condition of stationarity. Okay. So this is a condition of stationarity. Okay. Now, what we have to do? We have to integrate by parts. I will show you how to proceed. So this next step requires Gauss theorem. So I write dw over dFIA delta FIA. And I remember that this is equal to the partial derivative with respect to xa of delta ki. I am commuting, the partial derivative with the symbol of delta. Okay? So I have now integral over c star of dw over dFIA d over dxa delta ki. Okay? I can apply Leibniz rule for derivation. So if I have this quantity, I derive this quantity using Leibniz rule. I have the derivative of the first times the second not derived plus the first not derived times the second derived. Okay? So in order to have the equality, here I must subtract d over dxa of dw over dFIA delta ki. And I have the equality. You agree with this? Yeah? So I have now integral over c star of d over dxa dw dFIA delta ki minus the integral over c star of d over dxa. This is Piola stress PIA delta ki. Okay. Now d over dxa of a vector, let us call it VA. This is what is called the divergence of the vector. Forget about the I index because it is saturated. So our vector VA, the one which we consider in the application of Gauss theorem, is defined in this way. Okay. Remark how elegant is contravariant covariant notation. I'm writing formulas which are automatically correct. So this is P. Here I was wrong. There's P here as the other index. You have I below and A at the top. Here you have PIA delta Ki. Okay, so you have the saturation of Piola stress with the virtual displacement delta Ki. Okay, now Gauss theorem says that the integral of the divergence is equal to integral over C star of VA and A. Gauss theorem says that on the boundary of C. Gauss theorem says that if I have a domain omega, and I have the boundary of omega, and I have a vector field defined in omega, when we will try to do some fluid mechanics, we will discuss this stuff. And I have integral of d over dxa of the vector VA in omega. This is also integral over omega. This is also called divergence of V. This integral, this is a volume integral, is equal to the integral on the boundary of VA and A. This is the flux of V at the surface boundary of omega. So in every point of the boundary of omega, you have the normal, you have the vector V, you calculate V dot n, and you have the flux of V at the boundary. Now, Gauss theorem tells you that the flux at the boundary is equal to the integral of the divergence. Okay, so Gauss theorem allows you to transform a volume integral into a surface integral. Okay. So if you have troubles with this, let me know. We will try to go in deeper details about Gauss theorem. Everybody having studied electromagnetism should know about Gauss theorem, which, by the way, is applied everywhere in physics. Okay. So we can transform the first variation. So we have that the first variation of the deformation energy after all these calculations is equal to the integral of the divergence, okay, which is integral on the boundary of C star of V dot n. V is equal to P AI and V dot n is equal to P AI delta Ki n A in components. Okay, plus this was after the application of Gauss theorem, this volume integral, and then I have here d over dxa p I a delta ki. This is the divergence of tensor P dot delta K. And I'm sure that you start recognizing something which you have already seen in classical strength of material courses. Okay. So now let us write explicitly component-wise this another time. I have integral over d c star p I a n a delta ki plus integral over c star of d p a I dxa delta ki. And this has to be equal to 0 for every delta ki. Now, what we did, a pure integration by parts, because we applied the standard techniques of integration by parts. Okay, and we performed and imposed a stationarity condition. Okay, so key 0 is a minimum, implies that for every delta ki, the integral on the boundary of C star of P I N A delta ki plus the integral over C star of d P I A dxa delta ki is equal to 0. Okay, it is 10:40, so let us make a resume and we will move another step. Believe me, you will not be able to use COMSOL in an efficient way if you don't understand the theory which I am presenting you now, okay? So let us remember that the admissible placements have value key x equal x in the first part of blocked boundary, and key x equal x plus u0 of x in the second part of the boundary. Okay, so when I calculate delta key, I must, when considering delta key, I must verify for key plus delta key the same boundary conditions. Okay. So what happens? Delta key of x plus key of x has to be equal to x in delta c star 1, and delta key x plus key of x must be equal to x plus u0 x in delta c star 2. But as key 0 verifies these boundary conditions, this implies that delta key x is 0 in delta c star 1 union delta c star 2. You cannot vary looking for minima. You cannot vary the position of the imposed displacement. And this is what I did when I draw, I said, this is delta C1 star. This is delta C2 star. And I write the shape and the variation of the shape. But the varied shape must have the same boundary condition. So in this formula here, the integral over C star minus delta C star 1 union delta C star 2 appears, because here you have PIA and A delta key I. So this is the only part which remains alive in our surface integral. Okay, then you have plus integral over C star of d over dx a p I a delta key I equals 0 for every delta key I. Okay. Okay. So we can say that for every virtual displacement, for a virtual admissible displacement, the work spent by P on delta key on the boundary plus the work spent by div P on delta key in the volume must vanish. And this is the esoteric statement which drives crazy many people. because sometimes it is very convenient to postulate this. Okay? But this is a consequence of the minimality principle. We will see how we can generalize this in the next lectures. Okay, so as this lecture was rather heavy, I think it is better if we stop here now. And I am open to comments. You know, I've seen many people disappearing